I never know when I switch things around. All right, so yeah, let's talk about breadth first traversal of our binary trees. So first, let's just look at the algorithm, and then let's talk about how we implement it. So we have a queue. There's a head over. I'm put the head on the left, and we have our output. So our algorithm, remember, is insert root, and then we do the following loop. Remove whatever's at the head of the queue, let's call that T. Print T's data. And then insert T left and insert T right. And go back up to the top of the loop. So how this plays out, we start off with the root of the tree, which is a 10. We insert that into our queue. And then we come through our loop. So our loop says remove the head of the queue, so that disappears, and T is 10. We print out its data. We insert its left child, which is 5, and we insert its right child, which is 20. Go back to the top of the loop. So remove the head of the queue, which is 5, so T is 5. Print its data. Insert its left child 4, insert the right child 7, go back to the top of the loop. And we just keep doing this. Remove the head is 20, so T is 20, print the data. Insert the left child, which is 15. There is no right child, so we don't insert anything there. And what we have in the queue at each point is basically what's on the next level of the tree. Right? So right now we're adding things from this third level, 4, 7, and 15. So when we remove the 4 and we print that out, if it has any children, we're going to add those to the back of the queue. There's no left or right children here, so there's nothing to add. Remove the 7, so T equals 7. Print out that data, there's nothing to add. Remove the 15, so T is 15. Print out that data. And now we take its left child and its right child and add those to the queue. And if we had more stuff here, that would have been built up in the queue. We would have removed those and printed them and added their children. So each time we're going through, we're pulling off items and printing them, but we're remembering what their children are, so that after we're done with everything on this level, we start printing out those. And as we're printing out those, we're remembering what their children are and putting them in the back of the queue, so that eventually when we're done with this level, we'll move on to their children. So the algorithm itself, does that make sense? Just the high level, how we do this on paper? So let's look at what this means in code. So your queue is a linked list. So there's a sentinel node, which points to the head of the queue, which points down and eventually points to the tail. So here's the head, and here's the tail. And so I'm going to call this thing a queue node. You can call it what you like. But what does a queue node look like? So in PA3, our queue was supposed to store integers. So our queue node contained a piece called data that was just an integer. Here, even though I wrote integers, these are not integers. These are pieces of our tree. These are nodes in our tree. If I just store a 5, then when I remove a 5 and I say T equals 5, what do I mean by T arrow left? Right? Integers don't have left and right subfields. So these things that I'm storing in the queue, this is actually the node 5. So that when I remove it, I can say what's its data value, what's its left field, what's its right field. So the linked list, which builds up our queue is going to contain something like a struct tNode pointer called data, and then a struct qnode called next. So each of these things basically points to a tree node. And so our struct tree node, in this case our data is just an integer, and then we have struct tNode pointers left and right. So we've got some composite data types here, but your code doesn't really change for the queue. When you declare the nodes in the queue, you make it a struct tNode star instead of an int. But that's kind of all that changes is the variable type. Because we don't do any comparisons. We're not looking for greater than or less than or anything like that. So your remove function should return a struct tNode star. Your insert should accept a struct tNode star. And that's kind of the only difference, is just the types of variables involved. But if you draw the full picture, right, each of these nodes has a little tree in it, basically. And it's not actually a tree, it's a pointer to the root of a tree. But if we were to think of this as a tree, at this point our queue would look something like this. I don't know if this is helpful or not. When we seed the whole process, our queue looks like this. The first thing in the queue is this. Don't worry about reading it. Right, but it's a little tree in there. And when we say t equals remove, t is equal to effectively this tree. Right, and that gets removed from the queue. We print out t arrow data, that's 10. And then we insert t arrow left. Well, t arrow left is this tree, and t arrow right is this tree. Right, so you can think of it as that's what your queue is holding, is these actual trees. So when I remove this, I'm going to print a 5. I'm going to put a 4 and a 7 singleton trees in. When I remove this, I'm going to print a 20. I'm going to add this 15, 13, 17 tree, and nothing for the right. So does that make a little more sense? Yeah? Okay. So it's one of these things that if you really think about it and you really start trying to visualize a linked list whose data elements are nodes containing integers and pointers, it gets kind of confusing. But if you can abstract up a level or two and just think of this as a queue of nodes, tree nodes, right, then it becomes a little more straightforward, perhaps. And this is pretty typical of things you'll see again and again. We'll do this a fair amount in 223, where we'll have structures containing other structures. And in Java, we'll actually talk about a concept called generics, which is basically the realization that a queue is a queue is a queue, whether it's storing integers or characters or strings or pointers to tree nodes. The basic mechanics of the queue doesn't change. Right? The way we insert is we find the tail and we create a new node and we point the tail to that and we set it to null and so on. And a generic is a way to basically write one set of code that works with multiple data types. So we can write our code generically, and then when we want to use this queue, we just say, okay, and I want my data to be an integer or a character or a string. And we don't have to keep changing the code. Yeah?
Following this question about before, I wanted to ask about the loading function.
Okay.
Are we not supposed to be redirecting the nodes to another node to delete, like, the root of each subsection of the tree? For example, if you put 5 and 2, you delete 5.
What's your example tree?
Just put down any number you want. 5, 2, 3, just so you get the triangle going.
So you want like something here, something there? Okay. So like that?
Yeah. And then let's assume that that's just a subsection, like another tree.
Yeah, so there's other stuff up here.
But
Okay.
if you delete that 5, you don't want us to be redirecting the 2 and the 10 to something else.
So our code has sort of 2 pieces to it. 3 pieces. If the tree's null, we don't do anything. If we're not trying to delete the root, okay, we're going to say, okay, delete from either the left or the right subtree, and then replace the left or right subtree with what delete returned. So the only real thing our code is doing is always deleting a root. So let's talk about that first, and then let's talk about what I said before about linking these up. So how do we delete the root of a tree? Assuming there's something on the left, find the largest thing in the left subtree, make that the root. That's the whole algorithm. So in this case, the largest thing on the left is a 2. So this is what our tree looks like after we delete the 5. And we took the largest thing on the left and we replaced the root with that. Now if our tree looks like this, the largest thing on the left is a 4. So here's what our tree looks like after we delete the root. We just took that 4 and moved it up to the root. If our tree looks like this, largest thing on the left is still a 4, so 4 is going to be the root. But we've got to do something with this 3, right? So if the thing that we're moving up to the root has a left child, have its parent adopt that. So this is what the tree looks like after we delete the root. And those are kind of the 3 cases where we're deleting a root and replacing with the largest thing from the left. There's an edge case like this where there's nothing on the left of the root, so we can't find the largest thing in the left because there is no left. And in that case, we just change the right child to be the root. So that's what the tree looks like after we delete the root. And if there was other stuff here, right, then that's still, right, so we really just say the root is here now. But the only time you do that is when there's nothing on the left. Any other case, find the largest thing in the left subtree, make that the root. Okay, so how do we tie that in to a larger tree? So we've got a root, we've got some stuff. So let me just draw generic subtrees, and somewhere over here there's some node and it's got, you know, some stuff under it. And let's say the number we want to delete is this number right here. Okay, so there's some stuff up here that's pointing to it, there's some stuff on the right. Okay, we're not deleting the root of this original tree. Okay, so what we're going to do effectively is we're going to find where the thing is that we want to delete, and we're going to say delete the root of this tree. Okay, doing something like this. And the tree that we end up with, we put that right here. So we don't change anything above this node, we don't change anything on the right of the root. We only change this tree whose root is the thing we're trying to delete. And we do whatever we have to do to delete the root, so replace this with the largest thing on the left. And when we're done, in our original tree, we replace this with this modified tree. So in practice, if you have something like 20, 10, 5, 12, 11, 18, 14, 16, 15, 13, I'm making this up now, and we want to delete a 12, okay, what's your code going to do? Ultimately, it's going to find the 12, and you're going to recurse, right? And at some point, you're going to recurse, and you're going to say, delete 12 from this tree. And so it's going to say, okay, find the largest thing on the left, that's 11. Make that the root. So 11, 18, 14, 13, 16, 15. And this is what your delete function will return. Okay, at that point, you had gotten down here and you said delete 12 from the root, and your delete returns this tree. This tree goes right here. Okay, and now you've deleted 12 from the original tree, but really you deleted the root from this tree, took the modified tree, and replaced this thing with it.
Will we ever delete the actual root?
Sure, if I had this tree and I said delete 20, it's going to delete that right there. So here's what your code looks like. So some pseudocode here. So you pass it a struct t node, and you pass it a number, and your delete function returns a pointer to a t node. It returns the root of the tree that you've modified. Okay, so if tree data is bigger than num, so your number is smaller than the root, you want to delete from the left. So delete tree left, delete num from that. But then set my tree left equal to that. So this says take the left subtree, remove number from it, and now make my left subtree equal to whatever I got back from delete. So take that left piece, remove the node, put that left piece back. Okay, else, if it's less than num, delete from the right subtree. Else, delete the root. And then when you're done, return the possibly new root of the tree. And if you assume that you're only calling this when you actually know a node is in the tree, you don't have to worry about the case where your tree is null, because you'd never be trying to delete from a null tree. So in your main program, you've got struct t node, my tree. And that's the thing that you're adding to, you're deleting from, you're searching from, and so on and so forth. If the user says d number, I'm going to do a call like this, my tree equals delete my tree, comma, whatever the number is that I got from scanf. So take that tree, delete the root, and then set my tree equal to the root of that new tree. So now if I do what you suggested, if I'm actually deleting the 20, right, my code would build a new tree with an 18 at the root, and it would return that 18, and this will set my tree equal to that 18. Does that make sense? It's one of those semi-magical things that when it works, it's beautiful, but the fact that it's magic makes it frustrating if it's not working.
Is it
Sorry? Delete is the hardest of them all, yeah. The breadth first traversal is tricky, but conceptually, you know, it's an initialization in 4 steps, and it's just getting the mechanics of the queue and the looping worked out. But the deletion has a number of special cases, which can be tricky to do. Right, so if there's no left subtree, that's a special case. Depending on how you write your code, finding the largest thing in the left subtree means starting at the root of the left subtree and moving to the right. But you need to know what the previous node was, so that if you have something like this, and you find 4 is the biggest node, you need to know what the previous node was. So you have to keep track of that so that can adopt anything on the left. But if there is no previous node, if this is the largest thing, and maybe it's got something on the left, then when you move this up to the root, you don't do anything to its left child, so that's another special case. So it's a few different versions to run through, a few different cases. But get it as close as you can. Don't break anything in the process, right? So, because delete's just one piece of it, and I know it's the hardest piece, so you definitely get points for it, but it's not startling or alarming or a really, really bad sign if you don't get delete to work perfectly, okay, because it is pretty complex. So do what you can. All right, other questions? Did everybody get the ODP done? So you realize you wrote like an entire try package in like 3 days, right? Which is pretty cool. Okay, cool. So let's Heapify. I don't know if this is a word. It is now. Heapification. Sounds like a Red Hot Chili Pepper song. So heapification or heapifying. So this is the question of how do we build a heap from a set of data? Suppose we want to use what we're doing with heaps to sort data. We know that if we take our numbers and we build a max heap, then we can start pulling out the root, moving the last element up, down heaping, and we can do this successively and get our numbers from largest to smallest, or we can do a min heap and go from smallest to largest. So you did this on the board, right? You took a set of numbers and you built a heap out of it, and then you pulled them out and they came out in the proper order. So that's one way to sort things, but it's expensive, relatively, because insert is an order log n. And so if you want to insert n things, it turns out to be order n log n. And similarly, removal is log n, and so n removals is also n log n. And so our total time to do a heap sort would be 2n log n, so it's just order n log n. It's better than bubble, but it's on par with merge sort. So we can improve on this by bringing this order of complexity down. The removal is still going to be n log n, but removing is really, it's an instantaneous process. Grab the root, and then you go ahead and you rebuild your heap. And it's possible you might be able to do that in the background. You might be able to pull off the largest number, and then while you're doing something with that, have the heap being readjusted in another process. But let's look at this business of building a heap. So it turns out there's a better way to build a heap, which is to take whatever your input numbers are and just turn them into a heap-shaped thing without worrying about the heap property. So just use the second characteristic that we want things to have the shape of a heap. So let's do that. So let's say we want the numbers 20, 10, 5, 15, 4, 11, and 7. All right, first thing we're going to do, we're just going to throw these into a heap shape. So 20, 10, 5, 15, 4, 11, 7. Without any regard for the heap property of each node. And remember, we're talking max heaps. Okay, so now we're going to heapify. And heapify means basically going through node by node and making sure that each node satisfies the heap property. Okay, so start with a 7. Does that satisfy the heap property? Does it have a child that's bigger than it? Right, so it satisfies the heap property. Right, 11 satisfies, 4 satisfies, 15 satisfies. Everything on that bottom row is going to satisfy the heap property because it has no children, so it can't have a child that's bigger than it. Right? All right, so done, 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 done. Let's come up to the 5. Does 5 satisfy the heap property? Right, so it's not bigger than both children. So swap it with the largest child. And then down heap the 5, and 5 satisfies the heap property, so we're done. Okay, let's move to the 10. 10 does not satisfy, so swap with the largest child, so make this a 15. And a 10, 10 satisfies the heap property. And now come up to the next node, which is 20. 20 satisfies the heap property, and we're done. We got a heap. All right, that felt a little too easy. Let's go really pathological. All right, and we want a max heap out of this. Again, this, they all satisfy the heap property. 3 does not, so let's swap with the largest child. So make that a 3 and a 7. 2 does not satisfy, so swap with the largest child, make that a 5 and a 2. And now look at the 1. Does not satisfy the heap property, swap with the largest child, which is 7. Move down, 1 does not satisfy, swap with the largest child, which is 6. And we got a heap. 7, 6, 1, 3, 5, 4, 2. Does this seem pretty easy? And at first glance, this might look like n log n, but it turns out this is actually order n. And you can find lots of proofs online. The proof is involved. But here's the intuition behind the proof. Notice that when we started this, more than half of our numbers were already satisfying the heap property. Right, we had 7 numbers, 4 of them we didn't have to do anything with first time through because these all satisfy the heap property. So 50% of your numbers you don't even have to look at. On our second level, these might violate the heap property, but worst case we have to swap with one child and then we're done. Because once we swap with one child, they're going to be on the bottom level and they'll satisfy the heap property. So 50% of your numbers you don't have to do anything with. Another 25% you at most have to do one operation. So 3/4 of your numbers, on average, you're doing less than one operation. And the only time that you're actually doing log n operations potentially is with one of your numbers. And that's the root. And there you might have to adjust all the way down and go through log n. So it's really not n log n. It's a little bit times n over 2 plus a little bit more times n over 4 plus a little bit more times n over 8. And if you add those up and you do the series, you end up, this is order n. Whereas inserting one at a time and reheaping at each point turns out to be n log n. So this is a more efficient way to build a heap. All right, questions on that? All right, so go to the board. Let's heapify. And then we're going to talk about storing these also at the board. So yeah, I'm giving you a tree here to work on. All right, let's heapify this thing.
30 0 50 50 9 8
So now we're down or I was supposed to follow how we did it. They start at the bottom.
You always start from here.
So let's start here.
So remember, you always start with the bottom row, rightmost number, and you move across, and you slowly move up one row at a time until you get to the root.
Look at this one. This follows the, it has no children, that's bigger than it. This has no children, that's bigger than it. This one has no children, that's bigger than it. But this one fails that test. So now we're done with this row. This
one has a
No. You have to go to the left. No. Yep. This becomes a
All right, so there you got to make an adjustment. So you want to swap it.
Like this, we knows our process.
And then take that thing that you didn't replace, that has 5. Okay, so you're done. Keep going, then you go to 2. You just keep working your way up. You put like a wall there and you still get first adjustment you made. Okay.
I wouldn't mess with this.
Have you played? No, I
still have my Greek emotion.
Yeah.
All right, we'll make a harder one. Try that. Okay, cool. Makes sense? Where'd 7 come from? Okay. We got 1. All right, good. You always start from the right. You start at the bottom level and you move right to left. Then you go up and move right to left. Okay, cool. All right, so you can make another one and play with that for a minute if you want.
That's like where it started to fall off, I think. I liked that, and then after that, I went
Yeah, so basically, and then there's balance, and then there is doesn't matter, right? Like,
Nope, don't change left and right. Just swap the
Yeah, doing it this way is a lot more efficient.
Whichever one is the larger. That's the only discriminator, is which one is the largest child, that's the one you have to swap with.
I don't.
Do you have any idea?
That's
It says a few Hopefully it's just
Yeah, it's a maxi. So, where's the first one that you had to adjust?
yeah, so let's say 30.
It's basically 50 satisfies the heap property, but doesn't have any children bigger than it. 0 doesn't have any children, so that's fine. 30 is bigger than its child. But 1's the first node that violates the heap property. So everything else will be the same, all you're doing is swapping those two. When you're deleting those. Alright, so you're starting down here and you go up here and you go off. And each point if a node violates the heap property, it's the largest child. You're not going to do
Oh, and how do
Okay.
There was a lot.
Alright, cool. You make another and play with it if you want. You didn't prove 1 plus 1 equals 2.
And why would I not get
terrible.
Yeah. Alright, yes, that looks good. Makes sense? Okay. Right. Yeah.
It's like, yeah, something's going on.
Yeah.
Yeah, well, it wasn't worried about that.
Right.
It was.
So the room must be
Everything's got to be smaller than its children.
Start off here.
Oh, nice. Need that for vehicle.
That's kind of cute. You start off from here. Next number?
Turn it into a min heap.
Did you have like
So min heap, every number's got to be smaller than its children. So take this and divide it into a min heap.
So do we do the same picture on the right and then keep moving around?
So same thing, start here and move over until you get something that violates the heap property.
Oh.
See where that gets you.
No, that's fine.
Okay.
Let's see. So
if you've got this done and you want another challenge, take your max heap, turn it into a min heap. So exact same process, but each node has to be smaller than its children. So see what it takes to turn your max heap into a min heap.
Oh, we did it wrong.
And yours is obviously right, because the user is the answer key there.
We're supposed to switch from one to the
Okay.
Yeah. Oh. Wait, no. We ignore this for now. We didn't yeah. So we start here. This is violence, because they don't have children. So we move on to this one, violates nothing. Now we have to do this one. We didn't do this one first. So look at this one. This was the smallest, so we put this one first. No, we look at these two numbers simultaneously, and we pick the one that's smallest, and we flip it. No, because one has to be smaller than 10 and 9. Yeah. Okay, so now we're looking at this number.
So,
Yeah, but we have to start from the right first.
when you're programming it, then
So we put the 0 up here.
you start off and then you don't have to
And then now you look at this number. One's the
start off there
smallest.
and then whereas if you're
And
doing
now we're going to
work your way up.
And now,
Okay, so if you start off here, at this point, isn't this be all set?
No, if you swap the 3 to 99, now look at the 3 and see if it violates. If it doesn't swap.
You didn't even.
But you only have to, when you swap a node, right, you check the new position of that node, you violate swap, and you're just going to work your way down. So either it satisfies or it has no children, in which case it satisfies. You
really like it.
You don't have to go back and redo the whole process. All right, so the max heap, so you got to go ahead and
let's hope Nick comes by and gets the right one.
Okay, cool.
Okay, now start from the top.
I wonder if we actually did this right. So we started to the right, and then since they didn't have children, we skipped these ones. And the 10 switch would be
You had a 0 up here. You got here, you probably swapped with the 0. And then the 50 here, you got to swap with the smallest child, which was 2. That went down there, and 2 went up there. So yeah, that looks perfect.
okay.
Cool.
We probably should have switched with a different brand so we didn't have to our steps.
No, that's good. Cool. All right, so we'll talk about implementation tomorrow.
Yeah, go ahead.
Okay. Cool. Yeah. Okay, cool.
I'm gonna rack my brain trying to write the heap function.